Number 1 asks, does the equation 2y squared minus 3x squared equal 2 define y as a function of x? So if we can solve this equation into the form y equal some expression with x's, like y equal f of x, then y will define, then the equation does define y as a function of x. So let's just try solving it. And let's see, we have, let me write down 2y squared minus 3x squared equal 2. Let's add 3x squared to both sides, and we get 2y squared is equal to 3x squared plus 2. And we can divide both sides, let's say, by 2. Y squared is equal to 3x squared plus 2 over 2. But now when we try to solve for y, we have to take the plus minus square root of both sides because of this y squared here. So because of this plus minus, we see that every x value that we substitute in has two corresponding y values, one for the plus and one for the minus. So the answer here is no. Remember, every x value can correspond to only one y if y is a function of x. So here the answer is no, and mainly the problem was this y squared over here. In number 2, we want to find f of 3a minus 4, so instead of x, we're going to substitute 3a minus 4. All right, so let's write on the left, we can write f of 3a minus 4 is equal to 7 minus 2. Here put a set of parentheses for x, so now we have a place to write the 3a minus 4 right there in the parentheses. The parentheses are important because now we're going to expand. We're going to multiply through by minus 2, multiply through the parentheses. So we get 7, and here we have minus 2 times 3a, that's minus 6a. And then here we have minus 2 times minus 4, so that's plus 8. And let's just simplify this. Let's add the 7 and the 8, so we have 15 minus 6a. In number 3, we want to find the domain. Remember, the domain is all possible x values that give us a corresponding f of x value or y value. We can substitute in anything here and come up with a corresponding f of x value, excluding x equal 8 and x equal minus 9, because those values, 8 and minus 9, make the denominator 0. So the domain, sometimes we use the capital letter X for the domain. We can write as follows. The domain is equal to all x values except x cannot be equal to 8 and x cannot be equal to negative 9. In number 4, again, we're finding the domain, and here we have a square root, and the square root's in the denominator. So because of the square root, we know that everything underneath this square root has to be greater than or equal to 0. But because the square root's in the denominator, it can't be equal to 0. So we say we require that x minus 3 be strictly greater than 0, or x be greater than 3. And that's our domain. In number 5, we want to know if this point is on this graph. So we're just going to substitute in for x and y. Okay, so let's rewrite this equation, and instead of x, I'm just going to put some parentheses. And instead of y squared, put parentheses squared. And we're going to substitute in minus 1 over root 2 for x and 1 over root 2 for y. And we're asking, is this equal to 1? So when we square this, we get 1/2. And when we square this, we also get 1/2. And 1/2 plus 1/2 is equal to 1. So the answer is yes, the point is on the graph. And number 6, we're looking for x-intercepts. So in order to find an x-intercept, what we do is we just set y equal to 0 and solve. So let's do that. Y is really, in function notation, we write f of x for the y value that corresponds to x. So we're going to set f of x equal to 0. So we have 0 is equal to x cubed minus 9x. Factor out an x over here. And we have 0 is equal to x plus 3, x minus 3. And we solve this by setting each factor equal to 0, and we get 3 solutions: x equals 0, x equal minus 3, and x is equal to 3. So we have 3 x-intercepts. In number 7, we want to find all x such that x1 is the point on the graph of f of x. So in other words, this is the x value and this is the y value. So if we substitute, we're just going to substitute y equal 1 and find the corresponding x values. All right, so we're going to put a 1 here for f of x. So we have 1 is equal to x squared minus 9x plus 15. This is a quadratic. Just let's set it to 0. Subtract 1 from both sides. So here we get x squared minus 9x plus 14. And we're going to try to solve this by factoring. So we can factor this as x minus 7 times x minus 2. So we have 2 solutions, 2 x values. All right, so we have 2 comma 1 is the point on the graph, and also 7 comma 1 is a point on the graph. And in number 8, we're going to explain how the vertical line test determines if a curve represents a function. So if we have a curve, let's say this is x value 2, and if we look at the point above x equal 2, let's say this is 3, and if this is 0.23, then this curve represents a function where 2 is related to 3. In other words, the value x equal 2 corresponds to the x value 2 corresponds to the y value of 3. All right, now if we have a curve like, let's say this, for example, and if this is 2, and if we look above 2, we see, in this case, we have 2 points that correspond to x equal 2. Let's suppose this is, let's say this is 1, and this is, let's say, 4. And so in this picture, we have that the x value, when x is equal to 2, y is equal to 1. And also when x is equal to 2, we have y is equal to 4. So we have 2 y values that correspond to x equal 2. So this curve does not represent a function. And one way we could see this is by doing what we call the vertical line test. If vertical lines always cross the curve at most once, then every x value will correspond to only one y value. Here we have a vertical line that crosses the curve twice, and this does not determine a function. So that's the vertical line test. Just see if vertical lines cross a curve once, then the curve represents a function. More than once, and the curve does not represent a function. So this one is a function, and this one's not a function.